Hello everyone, welcome back to our channel. In today's video, we will be discussing about our new lesson entitled Exponential Functions and Exponential Equation. So I'm very sorry guys if it took me a while to upload a new video because I've been busy so far. So let's get started. So hello guys, our next lesson would be exponential functions. Okay, so please bear with me, and again I apologize for uploading a late video lesson because I've been busy here. So we have here exponential functions. So we are done discussing about functions and inverse functions. Now we are going to move on to exponential functions. Now we have here the objectives. The first is learn the brief history of exponential functions. Second, to use the properties of exponents. Two, we have here number one, simplify exponential functions. Number two, solve exponential equations. And the third is to sketch graphs of exponential functions. But we'll be focusing on simplifying exponential expressions and solving exponential equations in this video lesson. So what is then exponential function? So we have here a polynomial function has the basic form f of x is equal to x cubed. Okay, so we've been discussing about polynomial function. Now how about an exponential function? So it says that it has the basic form of f of x is equal to 3 to the power of x. Now, what have you noticed with the differences between what is the difference between a polynomial function and an exponential function? Now, basically, you have here, if f of x is equal to x cubed and f of x is equal to 3 to the power of x, here, the exponent and the base are interchanged. An exponential function, the variable is at the exponent. An exponential function has the variable in the exponent and not in the base. So the general form of an exponential function is f of x equal to n to the power of x, where n is greater than 0. Now, who invented exponential functions? Now, have you ever asked yourselves who invented exponential functions? So we have here, exponential functions were created by two men. We have John Napier and Jules Borgy independently of each other. Napier was from Scotland and his work was published in 1614, while Borgy, a native of Switzerland, developed his work in 1620. Although Napier and Borgy are generally credited with the invention of exponential functions, what they actually created is quite different from modern exponential functions, also known as logarithms. Exponential functions are used in many different disciplines, from astronomy to chemistry. Napier developed his logarithm theory based upon algebra, while Borgy developed his based on geometry. The commonly known exponential function is defined as a base number with a raised exponent, also known as a power. Now, there are properties of exponents that you are already exposed to when you were still in your junior high school. So let's take a look. You have here a to the power of x times a to the power of y. Remember the dot at the middle signifies multiplication operation. Now, if you have this expression granting that you have common base, which is a, this is product rule. All you have to do is you write the common base, then add their exponents. You have x plus y. So if you have this expression a to the power of x times a to the power of y, that is equal to a to the power of x plus y. So this is very simple. Let's proceed to the second one. This is called power rule. So we have here an exponent inside the parentheses and outside the parentheses. So if you have here a to the power of x being raised to the power of y, this becomes a to the power of xy. So all you have to do is multiply the exponent inside and outside the parentheses. And just simply copy the common base. or the base given. This one, you have here the quantity of AB raised to the power of x. Okay, as you've noticed, there's no exponent inside the parentheses, but it's understood that the exponent is 1. So we have here, all we have to do is distribute. So we call it the distributive property. We are going to distribute the exponent outside the parentheses to each variable or constant inside the parentheses. So this becomes, the quantity of AB raised to the power of x becomes a to the power of x times b to the power of x. Okay, let's proceed. Let's have this fraction. Okay, a fraction then enclosed in a parentheses with an exponent outside. So all we have to do, the same process. Okay, so all we have to do is simply distribute again the exponent in both numerator and denominator. So this could be like this, a to the power of x over b to the power of x. So if you have here a to the power of x over a to the power of y, quotient rule. So we have to be very careful to try to look at the base. The bases of the both numerator and denominator, they should be in common. So the base is common, which is a. All we have to do is to subtract. So you have a to the power of x minus y. Next, if we have here a to the power of negative x, okay? Remember, I've told you last time that in your final answer, there must be no negative exponent. And if you ever encounter a negative exponent, you have to simplify that one to make it positive. So a to the power of negative x is equivalent to 1 over a to the power of x, meaning you're going to get the reciprocal of this one, then the exponent would automatically be positive. If it's like this, 1 over a to the power of negative x, if the a to the power of negative x is in the denominator, the moment you place that on the numerator, the exponent becomes positive. So this is equivalent to this one, a to the power of x. Okay, let's proceed to another example. If you have here a to the power of x over y is equal to the white root of a to the power of x. Remember before when I told you, if the exponent of a particular base is a fraction, then this will be they call it white root, is the index, the denominator is the index of the theoretical symbol. Then you have a to the power of x. The numerator of that exponent becomes the power or the exponent of the base. So if we have here a to the power of 2/3, for instance, this is equivalent to the cube root of a squared. Okay, look, the denominator is the index. We wrote that here. Then write the base, which is a. Then copy the numerator of the exponent, which is 2. Okay, so a to the power of 2/3 is equivalent to the cube root of a squared. Okay, let us proceed. So properties of exponents, here we'll have an example. We have here 2 squared times 2 cubed is equal to, okay, first rule, you have common base, so we have to add the exponents. You have 2 plus 3, you have 2 to the power of 5. So multiply 2 by itself 5 times, that's 2 times 2 times 2 times 2 is equal to 32. Okay, how about this one? 2 cubed times 2 to the power of negative 6. Again, you have to add the exponents. You have here the same thing. You have to add exponents. 2 plus negative 6, that is 2 to the power of negative 4. And we are already clarified that we have to simplify. If there's a negative exponent, we'll make it positive. So the 2 to the power of negative 4 is 1 over 2 to the power of 4. And then we're going to expand or express this in simplest form. You have 1 to the over 16. Okay, multiply 2 by itself 4 times. Then we have the quantity of 2 cubed raised to the power of 2. So this is the power rule. All we have to do is copy the base and then multiply the exponent inside and outside the parentheses. You have 2 to the power of 6 because that is 3 times 2. and then multiply 2 by itself 6 times, the answer is 64. Okay, so always be very careful, because most of the time students, or you would tend to make some errors on multiplying 2 times 6 directly, meaning multiplying the base and the exponent, which is not supposed to be like that. Okay, you have to be very careful. That's common mistakes. So multiply 2 by itself 6 times. That's 2 times 2 times 2 times 2 times 2 times 2. That is 64. Okay, let's proceed. How about if you have 2/3? Okay, the quantity of 2/3 being raised to the power of -3. If you have a fraction and then it is being enclosed in a parenthesis, then raised to a negative exponent, to make the exponent positive, just remember you have to distribute the exponent to each both numerator and denominator, and to make this exponents positive, you are going to get the reciprocal of each, so it becomes like this one. So once 2 to the power of -3 once placed in the denominator, the exponent becomes positive. Same is true with 3 to the power of -3. Once it is placed on the numerator, it becomes positive. And to simplify this one, multiply 3 by itself 3 times, we have 27. And for 2/3, multiply 2 by itself 3 times, we have 8. That's 2 times 2 times 2, that's 8. For 3 cubed, you have 3 times 3 times 3, you have 27. Okay? Next, if you have 3 to the power of 7 over 3 to the power of 9, that is equal to, okay, common base, then you are going to subtract the exponent. Always remember that you have, when you subtract the exponent, you have to, the minuend will be the exponent of the numerator, and the subtrahend will be the exponent of the denominator. That's 7 minus 9. That gives you -2. So common base is 3. Copy common base 3, then raise to the power of -2. To make the exponent positive, you have here 1 over 3 squared. And to simplify that, that's 1 over 9. Okay, I hope everything is clear so far. Now let's proceed. You have 2 to the power of 1/2 times the quantity of 8 to the power of 1/2. Okay, remember the product rule, meaning distributive rule, like they have common exponents. Okay, so it's just the same as 2 times 8 then enclosed. Okay, it's just like this one. This is actually equivalent to 2 times 8 with an exponent of 1/2. Okay, remember, if you have common exponent, then it's just like the same as distributing the exponent to each of the constant inside the parentheses. So it becomes like this: 2 times 8 raised to the power of 1/2. 2 times 8 is 16, and then 1/2. Remember, 1/2 is the same as square root of 16. Okay, if it is square root, if it is 2 in the denominator, no need to write 2 in the index. It is considered that there is 2. We call it square root. And unless if it is 3 here, we call it cube root. That's the time we're going to write 3. If it's fourth root, we're going to write 4, and so on and so forth. Okay, and the exponent, the numerator is 1, no need to write 1. Okay, that's invisible. Then the square root of 16 is 4. Okay, let's proceed. So how about exponential equations? Now solve 5 to the power of x is equal to 125. So all we have to do, the target would be express both left and the right side of the equation with the same base. So if you have 5 to the power of x, 125 can be expressed in an expression or exponential expression with 5 as the base. So 5 to the power of x is equal to 5 cubed, because 5 cubed is 5 times 5 times 5. Okay, so once we are done expressing them the same base, we're now ready to equate all the exponents, both exponents. So x here, you write that, then you write the exponent 3. Therefore, x is equal to 3. Okay, let's proceed. How about if it's like this? Solve 7 to the power of x minus 1 is equal to 7 raised to the power of negative 1/2. Now, you've noticed that the base is already the same. So, no need to express it with the same base because in the given, it's already of the same base. All we have to do now is equate the exponents. So, we'll have x minus 1 is equal to negative 1/2. Then, transpose negative 1 to the other side of the equation. It becomes negative 1/2 plus 1. Negative 1/2 plus 1 is x is equal to 1/2. Okay. I hope everything is clear so far. Let's proceed. How about 8 to the power of x is equal to 2? Now, here the base is 8, here the base is 2, so we have to express 8 with the base of 2 because here we only have 2 here. So 8 is equal to 2/3. Then we have x as the exponent outside, and then we have here 2. It's understood that the exponent of 2 is 1. So we have here 2 to the 2 cubed times x. As the exponent, we have here 2 to the power of 3x. Then it's equal to 2 to the power of 1. Since we have the same base now, we're going to equate the exponents. We have 3x is equal to 1. Then x is equal to 1/3. That is dividing both sides of the equation by 3. Next, let's proceed. Solve 8 to the power of x is equal to 4. So 8 to the power of x is equal to 4. We have here express 8 and 4 with the same base. So 8 is 2 cubed, 4 is 2 squared. Then it becomes, remember, we'll just multiply this one, power rule. So 2 to the power of 3x is equal to 2 squared. Then we have 3x is equal to 2. Then x would be, divide both sides by 3, x is equal to 2/3. Okay, let's continue. How about the quantity of 1/3? X to the power of x is equal to 27. So remember, 1/3 can be expressed as 3 to the power of negative 1 because we need to, our target is to make both sides will have the same base. So our 27 can be expressed in exponential expression with a base of 3. So 3 to the power of negative 1, we have x outside as our exponent is equal to 27. 27 can be expressed as 3 cubed. Okay. So we have 3 to the power of negative x is equal to 3 cubed. Then we will equate the exponents. Therefore, we have negative x is equal to 3. Divide both sides by negative 1. So you have here x is equal to negative 3. Okay, let's continue. X to the power of 1/3 is equal to 27. Now, how about this one? What have you noticed with the expression? Okay, by the way, this is already not an example of exponential equations because for it to be an exponential equation, the exponent should be a variable. Here, the variable is in the base. So, but anyway, I want you to still know how to solve this one just in case you will caught yourself in this kind of problem. So you have x to the power of 1/3 is equal to 27 just in case like this. So again, it's not considered an exponential equation because the variable is now in the base. So if you have like this, how are you going to solve the value of x? So if x to the power of 1/3, all we have to do is to make the exponent equivalent to 1. So if it is 1/3, we need to raise to the power of 3 both sides of the equation. So we can have this one. Since it is 1/3, we'll multiply it by 3. So that becomes 1. And then if we're going to raise this to the power of 3, we're also going to raise to the power of 3 on this side because of the since it is an equation. So 1/3 times 3, that is 1. Therefore, the exponent of x is already 1. Then 27 cubed, that is 27 times 27 times 27, that's 19,683. So that is how you're going to solve for x if you have an expression like this. Okay, although this is not an exponential equation, however, if you caught yourself to be experiencing this or exposing this kind of problem, this is how you're going to solve. Okay. Now another, solve for x to the power of 3/4 is equal to 8. How are we going to solve this one? Still not considered an exponential equation because the variable is in the base. So this is how you're going to do it. Remember, the exponent is 3/4. Our target is to make the exponent equivalent to 1. So just multiply it by a reciprocal of 3/4. The reciprocal of 3/4 is 4/3. So we will raise each side of the equation by 4/3, so that it becomes like this. So x to the power of 3/4 being raised to the power of 4/3, then 8 to the power of 4/3. Okay, so this can be cancelled out, therefore the exponent of x will be 1. And then since it's 8 to the power of 4/3, remember the denominator is automatically the index of the radical symbol. So this becomes cube root of 8. Then the numerator of the exponent becomes the exponent of the base, or the exponent of the whole expression. Okay, so the cube root of 8, remember 8 is a perfect cube because we can think of a number that when multiplied by itself, it yields 8. And that number is 2. That is 2 times 2 times 2, that is 8. So the cube root of 8 is 2. Then copy raised to the power of 4. Then x is equal to 16. Meaning multiply 2 by itself 4 times. So that is 16. Okay, let's continue. Now, the general form of an exponential function is f of x is equal to n to the power of x, wherein n is greater than 0. G of x is equal to 2x. Now, let's have g of x is equal to 2 to the power of x. Let's have this example. So, it's just like this is our value of x. This is the function g of x. And this is the exponential function 2 to the power of x. So, if g of 3, meaning if we're going to substitute x with 3, what is the answer of the exponential function? So you have 2 cubed. This becomes 2 cubed. That is 2 times 2 times, so you have your 8. Okay. What if g of 2, meaning x is 2? That will become 2 squared. That gives us 4. How about g of 1? That is 2 to the power of 1. That gives us 2. How about g of 0? That's 2 to the power of 0. That gives us 1. Then g of negative 1. That becomes 2 to the power of negative 1. That becomes 2 to the power of negative 1. Again, how to make it positive? Just get a reciprocal. It becomes 1/2. The next would be g of negative 2. That is 2 to the power of negative 2. This becomes 2 to the power of negative 2 is equal to 1/2 squared. That gives us 1/4. Okay. So, to be let's express this in the table of values. We have g of x is equal to 2 to the power of x. Remember, this is our x values, our domain. G of x, our y. So, we are going to plot the values. If x is 2, g of x is 4. If x is 1, g of x is 2. If x is 0, g of x is 1. If x is negative 1, g of x is 1/2. If x is negative 2, g of x is 1/4. Okay. Now, this is the graph if you're going to plot the points. Okay. Then, let's proceed to another exponential function. H of x is equal to 3 to the power of x. Now, if x is 2, our h of x would be 9. That is 3 squared. If we're going to replace x with 2. If x is 1, our h of x is 3. That is 3 raised to the power of 1. If x is 0, our h of x is 1. That is 3 to the power of 0 is 1. Always remember that any number or any variable or any expression raised to the power of 0 is always equal to 1. If x is negative 1, that is 3 to the power of negative 1, our h of x would be 1/3. If x is, okay, for a moment, for you to, so you won't get confused again. So if x is negative 1, so this becomes 1/3. Okay, next, if x is negative 2, so since you have 3 to the power of x, and if x is negative 2, this becomes, remember to make the exponent positive, this becomes 3 squared. We're going to get the reciprocal, and then 1 over 3 squared, that is 1 over, what is 3 squared? That's 3 times 3, that is 9. Okay, so you have here 1 over 9. Okay, and this is the graph if we're going to plot all the points between the ordered pairs we have based on the table of values. Okay, so let's take a look. Now, if we are going to place the graph of the two exponential functions, g of x is equal to 2 to the power of x, which is the blue one, this one, and h of x is equal to 3 to the power of x, which is the red one, then we have exponential functions with positive bases greater than 1 have graphs that are increasing. As you've noticed from left to right, the graph is increasing. Okay, the bases are 2 and 3, which are obviously greater than 1. Okay, what else have you noticed? The function never crosses the x-axis because there is nothing we can plug in for x that will yield a 0 answer. So this is our x-axis, the horizontal line. And always remember that this function is never crosses the x-axis. It looks like it crosses, but it actually not. It's just only asymptotic to the x-axis. When you say asymptotic, meaning it will approach nearer and nearer towards the x-axis, but it will never ever intersect. Okay, so it says here that the x-axis is a left horizontal asymptote. It will just going to approach to the x-axis, but will never ever intersect. Okay, next, let's proceed. A smaller base means the graph rises more gradually. So between 2 and 3 as the base, or as the bases, okay, well, let's compare the graph. So this is the blue one. We have 2 to the power of x, this is a blue. And for 3 to the power of x is the red one. So a smaller, 2 is smaller than 3. So a smaller base means the graph rises more gradually. So this one, remember that the red one is 3 to the power of x. So it rises quicker compared to the function g of x equals to 2 to the power of x. Okay, next. So a larger base means the graph rises more quickly. So this one. So it is approaching up to the y-axis as the base is increasing or larger. So exponential functions will not have negative bases. Always remember that one, based on the definition, that n, or as a base, will never be equal to 0 or less than 0. It's always greater than 0. So in discussing about exponential function, you might be encountering this letter E, a base often associated with exponential function. So I will just give you a quick introduction about this one, but we will not be using this one because this will be discussed further when we are going to discuss with logarithmic function. So E is actually based on Euler, the mathematician, which this is approximate. Okay, this is the symbol for approximation. So approximately equal to 2.71828169. This is actually an irrational number. It is just simply like the pi, the value of pi. Remember, the pi is the ratio between the circumference and the diameter of a circle. Okay, and that is an irrational number. Same is true with Euler. It is also an irrational number, and this is the value associated to exponential function. So this is actually how it came from. This is the limit where x approaches to 0, 1 plus x raised to the power of 1 over x. But again, this is how it is being computed or estimated. This 2.7196 and 2.7169. So actually, this is how it is being computed, but we will not discuss this further because it will be discussed on the next lesson. So that's it. That's why we got this one, this approximation. So the number E, we have here Euler's number, or Euler, or other pronounce this as Euler's number, from Leonhard Euler. He's a Swiss mathematician and physicist. So the exponential function f of x is equal to e to the power of x is graphed like this one. So the exponential functions j of x is equal to 1/2 raised to the power of x. So if x is 2, what is j of x? Meaning substitute the value of x, we have 1/4, I mean. If x is 1, what is j of x? It is 1/2. If x is 0, what is j of x? It's 1. If j of x is -1, what is j of x? If x is -1, j of x is 2. If x is -2, the j of x is +4. Okay. So we were done with the previous graph of two examples of exponential function with 2 to the power of x and 3 to the power of x. This time it's 1/2 to the power of x. Let's take a look. How does the graph look like? So this is now the graph. After plotting the points based on the table of values, we have now this graph. So what have you noticed with the graph? How are you going to compare this with the previous examples? Now, exponential function with positive bases less than 1 have graphs that are decreasing. So the graph here is decreasing. Remember, 1/2 is the base and it is less than 1. Okay? If it is less than 1, the graph is decreasing, meaning from left to right, it's going down. Look at that. And it is asymptotic to the x-axis. Again, it will never intersect to x-axis. So why study exponential functions? You might be asking, how does exponential functions applied in real life situations? Now, there are examples of applications of exponential functions. We have exponential functions are used in our real world to measure growth, interest, and decay. Growth obeys exponential functions. Example, rumors. You're familiar with rumors, class. Okay? It really grows exponentially, spread exponentially. They can add, subtract, or multiply, or whatever. We also have human population, bacteria, computer technology, nuclear chain reactions, compound interest, and decay obeys exponential functions too. We have example, carbon-14 dating, half-life, Newton's law of cooling. Okay, I hope that you understand our discussion in today's video lesson. So at this time, focus on yourselves on how to solve exponential expressions and exponential equations. Now you're going to answer this assessment on your activity notebook. I will gonna read each problem. There are 24 of each. We have solved each equation. Number 1. 4 to the power of 2x plus 3 is equal to 1. Number 2. 5 to the power of 3 minus 2x is equal to 5 to the power of negative x. Number 3. 3 to the power of 1 minus 2x is equal to 243. Number 4. 3 to the power of 2a is equal to 3 to the power of negative a. Number 5. 4 to the power of 3x minus 2 is equal to 1. Number 6. 4 to the power of 2p is equal to 4 to the power of negative 2p minus 1. Number 7. 6 to the power of negative 2a is equal to 6 to the power of 2 minus 3a. Number 8. 2 to the power of 2x plus 2 is equal to 2 to the power of 3x. Number 9. 6 to the power of 3m times 6 to the power of negative m is equal to 6 to the power of negative 2m. Number 10. 2 to the power of x over 2 to the power of x is equal to 2 to the power of negative 2x. Number 11. 10 to the power of negative 3x times 10 to the power of x is equal to 1 over 10. Number 12. 3 to the power of negative 2x plus 1 times 3 to the power of negative 2x minus 3 is equal to 3 to the power of negative x. Number 13. 4 to the power of negative 2x times 4 to the power of x is equal to 64. Number 14. 6 to the power of negative 2x times 6 to the power of negative x is equal to 1 over 216. Number 15. 2 to the power of x times 1 over 32 is equal to 32. Number 16. 2 to the power of negative 3p times 2 to the power of 2p is equal to 2 to the power of 2p. Number 17. 64 times 16 to the power of negative 3x is equal to 16 to the power of 3x minus 2. 18. 81 to the power of 3n plus 2 over 243 to the power of negative n is equal to 3 to the power of 4. Number 19. 81 times 9 to the power of negative 2b minus 2 is equal to 27. Number 20. 9 to the power of 3x times 9 to the power of x is equal to 27. Number 21. The quantity of 1 over 6 being raised to the power of 3x plus 2 times 216 raised to the power of 3x is equal to 1 over 216. Number 22. 243 to the power of k plus 2 times 9 to the power of 2k minus 1 is equal to 9. Number 23. 16 to the power of r times 64 to the power of 3 minus 3r is equal to 64. And 24, the last number, 16 to the power of 2p minus 3 times 4 to the power of negative 2p is equal to 2 to the power of 4. Okay? So I hope you are going to enjoy in answering these exponential equations. And please make sure that you have to write a complete and thorough solutions for each item. Remember, no solutions means wrong. And to end this video lesson, let's have a quote. If your attention is divided by other distractions, multiply your mental traction by doing a bit of simple subtraction. Okay? Thank you so much everyone for watching, and please don't forget to subscribe this channel, and if you have some questions, please comment, just leave a comment in the comment section and enjoy answering. Thank you and God bless us all. Bye!